Hello, everybody. Thank you all for coming out tonight. My name is Zach Parrish. I'm the programming librarian here at the Bexley Public Library. Before we get started, I just wanted to give a quick plug for some library activities. If you haven't already heard, 2024 is the library's centennial. So we are celebrating our 100th birthday this year. We have a lot of wonderful programming. We have an incredible author series lined up, as well as some 100-theme music programs. So if you don't have a copy already, you can grab a Centennial Guide. We have them in the back. We also just came out with our spring program guide. So we have lots of wonderful programs lined up this spring. So if you don't have a guide yet, please grab one. That will show all the fun stuff we have coming up during March, April, and May. And speaking of some upcoming programs, this Sunday, March 10th, from 2 to 4 p.m., we have the Bexley Minority Parent Alliance Art Auction and Open House. So if you've passed through the lobby, you might have seen some art on easels. You'll have a chance to meet some of the artists as well as bid on some of those pieces. And the money raised at that event goes to supporting BMPA scholarships for Bexley High School students. And then next Thursday, March 14th at 7 o'clock, we have Mapping the Environmental Impact of Circular Thrift, which is a hyper-local thrifting and textile reuse model that was started right here in Bexley, and that will be with Lisa Goldsand and Ragul Sentil. And then we also have on Thursday, March 28th at 6:30 p.m., Michael Wilkos will be back from United Way of Central Ohio. We'll be back at the library for the third installment of the Next Chapter series. He will be moderating a panel on the future of transportation around Central Ohio. And there is a solar eclipse passing through. There is a solar eclipse passing through Ohio Monday, April 8th. So for those in person, you got your eclipse glasses. For those at home, we do still have some you can pick up at the lobby desk. This is a hybrid program really quick, so if you have questions at the end, if you're here in person, just raise your hand. I'll come around with the microphone. That way those joining at home can hear what was asked. And if you're watching on the live stream, you can type your questions into the chat at any time, and we will get those asked at the end. Tonight's presenter, we have Dr. Stefan Frank from, he was from the Ohio State University Department of Astronomy. He was born, raised, and educated in the south of Germany with a short but very meaningful stint in Edinburgh, Scotland, where he met his wife. He came to the US in 2000 after earning his PhD from OSU in 2008. And beginning his first stint as a postdoc, he returned to Europe, where he worked for 3 years in Marseille. And in 2011, Dr. Frank returned to OSU and Otterbein University, both in research and teaching, with a focus on outreach and education to the public. So I will turn it over to Dr. Frank, and thank you again for coming.
So I'm getting myself mic'd up. Is that working properly?
Good. Great.
The usual grumbling noises at the beginning of a presentation, as always.
Modern technology.
So here we go. Yeah, thanks, Zach, for this nice introduction. Sometimes when I hear these introductions, I think, man, sounds like a cool guy. I wish I could meet him and have a beer. And you can actually do that. You can actually come sometimes to Astronomy on Tap when it's here at the library, and you can have a beer with me and talk about all sorts of things that are related to science, and also all sorts of other things. I'm a big football fan, or you call it soccer, and beer. I'm also, as a German, I'm a beer fan. So. Obviously. So speaking of centennials, obviously, as you've heard, are you excited about the eclipse? Yes. Let's try this again. Are you excited about the eclipse? Yeah. So you can guess that more than 100 years ago, someone else was also very, very excited about eclipses, and that obviously is this man. Hands up. Do you know who this is? Yeah, it's 100% again. I've rarely had it that someone is like, never seen before, right? But actually, when you think about this, this is utterly amazing. You can show a picture like this all around the world to basically almost anybody who has gone to kindergarten. And everybody will say, yeah, that's Albert Einstein, I know. And then the next thing that people will say, oh, E equals mc squared, whoa, yay. And when you think about this, this is really, really bizarre in some sense. This is a theoretical physicist who lived and did his greatest work about 100 years ago, and yet he's still totally a household name everywhere in the whole world. He is a scientific superstar. There's probably, there are not many other people who are that recognizable. I mean, sorry, Swifties, Taylor Swift, you show them somewhere else, and then they'll be, not sure, it's a woman, singer, don't know. This guy, he's known everywhere. And that's kind of odd when you think about his profession, right? How many other theoretical physicists can you name? Well, I mean, the guy in the wheelchair who died recently, who was actually the successor of Newton a couple of 100 years ago, Stephen Hawking, he reached somewhat of that fame level as well, but he's nowhere near there. This is the global superstar, and the question really begs, why? What made him so famous? Especially because you can see when you look at this picture, it's very, very famous that he looks so pensive, and he has this very recognizable features, this bushy white hair, and looks grandfatherly and wise, and everybody knows him like that. At the time that he became famous, he was actually a much younger man, and he looked something like this. Not quite that recognizable, right? I mean, if I show that photo to you first, you'll be, it kind of looks familiar. And maybe, is this Einstein maybe or not? And so he only developed later on in this grandfatherly figure that we all seem to know. And of course, famously, he was playing with a camera later on when he realized that he can use his fame for certain endeavors. In politics, for example, he started playing with this. So he was actually a professional when it came to that. And then everybody knows this one photo where he sticks out his tongue, right? And it's like, and but really the question is, the theories that he developed, while they're very, very famous within the world of physics, they're kind of tough to understand. And at the time, there were people who claimed that there were only 2 or 3 people on the whole planet who even got the basics of some of his theories. So he was far removed from our everyday life and was doing things that are not really super relevant at all, and yet he became this super famous person. So I'm afraid I have to introduce you to his 2 theories in the basics, so don't run away. I'll keep it very short. These are the 2 big theories that, among others, made him quite famous, and that are the basis of today's talk, called the Theory of Special Relativity, which he developed in 1905. And as you can see here, he published that, and at that point of time, I mean, he was actually a Swiss citizen. He had emigrated from Germany, had relinquished his German citizenship, and was sitting in a patent office somewhere in Bern, and was just thinking about the universe and was writing these types of things, and got them published in a series of 3 very famous papers. This one of special relativity is the second one in the year 1905, which was this annus mirabilis, his wonderful year, basically, where he made big breakthroughs. And as you can see, they're all both in German, so I can highly recommend it, reading it in the original. It's super clear and super good. Let's get a start with the theory of special relativity. What's going on in that theory? It starts out very simple, and it turns out that Einstein is usually extremely good at making things as simple as possible. And he asks very simple questions and then comes up with 2 very important ideas. The first idea is that he says, look, for all observers, the physics that you describe should be exactly the same, right? It shouldn't matter when an apple drops like this, whether you're standing over there or over there, whether you're moving a little bit or not. It's the same apple that falls down, and that makes sense, right? The laws of physics should be the same. Well, we come back to that point in a few seconds. The second one is a little weirder. When he looked at what Maxwell did with Maxwell's equation about electrodynamics, he noticed that, in those equations, it always appears as if the speed of light in a vacuum must be the same for everybody. This sounds innocent, but completely contradicts our experience, right? So imagine, this is a slightly hypothetical thing. Imagine you have some archer in a train and some archer standing here on the ground. That train is going with a fairly high speed, and that archer is shooting an arrow at the target, and this archer standing here is also shooting an arrow with the same speed, releases that arrow. Which arrow will get there first? The one from the train, right? We all know this. I mean, you need to add those velocities together, and that means that the speed of the arrow for the man in the train is larger because there's the additional oomph that you get from the train running across there. Now replace this with light. Now they're shooting some laser cannon or something on here, and no matter how fast or slowly this train here goes, the weird result is that no, they will arrive at the same time. The speed of light for both of these observers will be the same. And this kind of totally contradicts our everyday experience. It's very bizarre. And yet, Einstein figured out that this must be how we need to describe the physics once we start moving a little bit faster than the speed of, faster and approaching the speed of light. This, when he thought it carefully through in his room there in Bern, in total isolation, and had enough time and wasn't bothered by anything, he realized that, this really leads me to completely rethink what we believe time and space is about. Before Einstein, everybody thought that, well, there's time, right? Clicking of a clock, tick, 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 and that's always the same. Shouldn't matter whether you're moving or not, that clock will always be the same. And space is also always the same. If I'm measuring out how long this distance here is, you should come up with the same result, right? And Einstein says, nope, that's not the case at all. It turns out that time and space depend on how you move. In fact, time and space, in this famous Lorentz transformation, I don't want to confuse anybody with math, but if you've heard about this, it's a very famous transformation that describes what you have to do when you want to describe different systems that are moving relative to each other. And what you can see here is that time and space are not independent of each other anymore. They're really what is called space-time. In one word, space-time. It's all connected. You cannot separate the one from the other somehow. And at first, you look at this, and Einstein looked at this and thought, yeah, okay, well, that's kind of, it really only matters very much when we move around with speeds that approach the speed of light. So our most everyday experiences tell us that, yeah, we don't need to worry about this. But it actually turns out that those consequences are quite odd when he really thought them through. First thing that he realized is that when we think things happen at the same time, simultaneously, you have to be very, very, very careful. And it turns out that this whole concept of stuff happening at the same time for people is terribly difficult. Another thing that he found was that, if I measure the size of anything while it's not moving, that's called its proper length, then I will come up with a different result that is larger than when the thing is moving. It's called length contractor in the diagram. You have your nice big car and you're driving along and all of a sudden you realize, whoa, it's shrinking. That would be really bizarre, right? Why don't we perceive this? Well, because all of these effects, according to his formula that he found out, only matter really a lot once you're approaching the speed of light. Another one that is very well known is basically the opposite of this length contraction. It's this time dilation. Clocks that are moving are ticking more slowly. So if you're standing there and if I'm counting the seconds, I can count and count and count, and a couple of years will pass. If I have a twin brother, hypothetically that I send in a rocket, so my twin brother born at the same time as myself, has the same age, we shake hands when he takes off and he goes hypothetically in a yet to be developed spacecraft that is really, really fast, and he zooms off to a far away stellar system, then turns around and comes back. Well, Einstein says, you were moving with a high speed, therefore your clock was ticking much more slowly. That guy will not be as old as I am back here on Earth. So when he comes back and gets out of that rocket ship, I'll be gray-haired, more gray-haired than even now, and he'll be, dude, what happened? This is not good. And, well, you see, this is universally known as the twin paradox. And I've always found that that is not really paradoxical, right? It's just a consequence of that formula. So it's not really, I mean, yeah, as long as you give up the notion that time is absolute, this is not difficult to explain. It must be happening. Oh, but let me tell you the story differently. Brother gets into the rocket, looks back at Earth, looks at me, and the brother tells the story differently. The brother says, no, dude, I am sitting here in my rocket, nothing is happening. You seem to be moving with a really high speed. According to Einstein, you should be getting younger, and I should be getting older. So well, which one is it now? What is? And that is the real paradox. You have to be able to explain that it actually turns out that it really is the fact that he, after coming back, is younger than I am. But you have to jump through a lot of hoops to really, really explain this very well. So that is the big paradox. So if you've heard about this paradox and think you understand it, you may have to think again, because it's actually much more complex than most people make it out to be. The crux of the matter, in fact, comes from the fact that we now need to address the question, why is that thing called the theory of special relativity? What makes it special? At first you think, oh, this must be something really cool, and later on he generalized it, but that's not that great anymore. The special relativity is a typical term that physicists use when they denote a clause that says, we need to be a little careful. Remember when I told you that the first postulate is that for all observers, things are that way and that way? Well, at the very first sentence, just like Newton in his famous book Principia, Einstein says, well, in the following, I will only deal with observers that are moving around that are not in an accelerated frame. So you cannot be accelerating. You can move around, but it has to be with uniform speed. As soon as you start changing your speed, so to say, all hell breaks loose and makes things very, very complicated. Newton already knew this as well. So here's one of those examples. So imagine you are inside this car here, and you have no idea what's going on outside, and you have no idea what's going on with this car. It's a very silently driven car. And from the outside, we look at that car, and what we notice is that the car is accelerating. So it's moving in this direction, and it's getting faster. And that means, well, there is inertia, and that mass that's hanging here cannot follow that motion quickly. And obviously what happens is that this mass that's hanging in there is staying behind a little bit. So from the outside, while we're not moving and we're looking at this and have the full knowledge of what's going on, we're like, oh, this is easy to understand. Physics is super easy, right? This is inertia, and there is no force and nothing. However, if you're inside this moving car and you don't know that there's acceleration, this would be weird, right? There's a string hanging down, and all of a sudden, that weight goes. You would conclude that there must be some kind of force that is doing that. And it turns out that Einstein says, nah, you can't argue that way. Newton also did this as well, but you can't argue that way because my theory is not good for these situations. It was good for other things, so he applied that theory then to mechanics. So he started out with thinking about electrodynamics, charges and things that are moving around. And then he said, oh, but I can also look at what happens when other things are moving around. And here is, so you can walk away today and claim that you have seen the most famous formula in physics ever, and you've actually heard what it's about. When you write down this theory, of Einstein, he realized that, oh, the energy of something that's moving and its momentum, so this is the momentum here, are intimately connected, but there's a term missing that nobody ever had thought of before. And that comes from this consequence of how you think about space and time. And what this means is that he can say, well, wait, even if a particle is not moving, if its momentum is zero, so it's just sitting there, there's still some energy in that particle. This is universally known as the mass-energy equivalent, and there's a boatload of energy in tiny little mass, because you're multiplying this with the square of the speed of light. The speed of light is an insanely large number, and therefore the speed of light squared gives you an enormous oomph. So whenever you have mass, you can convert that into energy. Einstein realized this early on, but he didn't realize that he can actually build a bomb with this, and that's the first thing that we humans do, right? I mean, you discover a great source of energy, and out comes this. So it's a little bit. He fought a lifelong battle then afterwards to try to curb our enthusiasm for these weapons. He also fought a battle after 1905, as I said. So he has said in his first sentence, he says, "Oh, this is just special, but let me." So what he wanted to do, he said, well, I want to understand in general what's going on, and now I need to allow these accelerations. So if I now want to think about space and time, I need to allow for the fact that things can be accelerating, right? I mean, we all experience accelerations daily, and so it's a natural impulse to try to do this. And he sat down and he thought, it's 1905. It took him only about 3 or 4 months when he first started thinking about relativity to get this result in 1905, the special relativity. And then he thought, okay, let me just sit down a little bit. He very quickly realized that this is mathematically much, much, much more difficult than before. The theory of special relativity, you can actually understand with high school math. I can teach anybody this Lorentz transformation. This is not rocket science. This is really just algebra. But this, oh goodness. I have tortured myself reading through some of these introductory textbooks where you have to do some tensor algebra, and you can rapidly see this is the beginnings, the start of some of that stuff. So Einstein himself, he struggled for 10, 11 years before he fully had a full grip on that and a full and good description. You can imagine that if a genius like Einstein spends 11 years, this is tough. This is not everybody's, oh yeah, let me write down on a piece of paper what's going on here. So this really, really required a lot of brain thought and special mathematics that are still being developed nowadays. So it's sometimes crazy that he invented fields of mathematics simply to describe gravity so that we can understand it. The basis, so aside from all of this math, I mean, I'm not going to throw this at you and leave you helpless. Aside from that math, you can actually fairly basically understand what this is all about by thinking about, well, he wants to describe gravity. But unlike Newton, he chooses a different pathway, right? Newton has always said that, oh, here's an object, they attract each other gravitationally because there's a force between the two of them, the force of gravity. Einstein doesn't think about forces at all. He thinks about space-time, and he thinks about the geometry of space-time. And what he learns is that, oh, masses influence the space-time, and space-time influences how masses act. And believe it or not, I brought a nice piece and fabric of space-time. I need now 4 volunteers. So, and they need to be strong because you need to be holding up space-time. So can you do that from here? Can you get just, yes, I have 3 already. I would say all 4 of you. Your task is very simple. You simply hold one corner of the space-time. And we keep it nice and tight. So pull nicely. And let's make it as straight as possible. That is, when we make it really, really straight, that is the fabric of space-time when there is no mass. Mathematicians call this, it's flat. So if you really pull it and make it really, really flat, then we would get a perfectly flat surface. There is no mass here, but look what happens when I throw in the sun. What happens right now? Well, the sun is, well, it's not quite heavy, right? It's actually very lightweight. I didn't bring my bowling ball because that would do bad things. But I brought a little bit of a weight, and let's put that weight in here. Whoa, you see? We almost broke space-time. That is my next experiment. So let's hold it again. There you go, and hold it tight. Yes, exactly. So nobody's ready for the breaking of space-time. And there we go. What we do right now is we are creating curved space, space-time curvature. Basically, this is how it's hard to do this in 3 dimensions. I can't wrap my head around 2 dimensions sometimes. I have trouble finding something on a map. But in 3 dimensions, this is also what's happening. Anything that is massive creates curved space-time. I brought some tiny little things. I haven't lost my marbles. I brought them with me. So look what happens when I put one object that has mass near the other object that also has mass. Whoop! Attraction. This is what Einstein realized. This is what gravity is about. There is no force or anything. It's just the curvature of space-time. That's nice and fuzzy. And around the sun, it goes around because of the curvature of space-time. So I'll try to do this. It's probably not going to work very well, and you can't see it anyway. But it swirls around like this. Now, Einstein realized that his formulae allowed things to be heavier and heavier and heavier. What happens when I make this really heavy? It'll get deeper down and deeper down, and at some point of time, the fabric of space-time rips apart, and we get a hole, a black hole, yeah. And yeah, well, that is the demonstration of curved space-time. This is very, very famous. Well, thank you for the volunteers who held up space-time so bravely. Great. And as I said, this is exactly what Einstein figured out. He predicted, therefore, the following. So here's another interesting thing that he found. He said, oh, look, that means, as you've seen, when there's gravity, things start moving towards each other. They accelerate. And what he found out was that he can always write things down in 2 different ways. This is called the equivalence principle. It's philosophically very, very important, and people have really started worrying about this already at around the time of Galileo Galilei. And the thing is the following. So everybody knows you're here on Earth, and you drop a ball. What does the ball do? It falls down. It's accelerated. Newton would say, well, because there's gravity, right? So there's gravitational potential because we are in the vicinity of the Earth. But imagine that you don't know that. Again, Einstein was very good about this thought experiment. He said, put yourself in a cage or an elevator or anything that doesn't allow you to look outside, and you do an experiment. You throw a ball downwards, and that ball accelerates downwards, and then you say, oh, I must be near a mass, like the Earth. That's why that ball is falling down. But Einstein says, no, no, it could also very well be, and I can always do this as an equivalent. That's why it's called the equivalent principle. I can do this in such a way that we are far away from any mass, somewhere in space where there's nothing around. If I have that rocket and that rocket accelerates in the right way, that ball will do the same thing, right? I leave the ball is not following the rocket because there's inertia, and that ball will seem, when you're inside the rocket, will seem to fall down. Although there is no gravity whatsoever. There's only acceleration. So you can equivalently describe this. This is a simple example, and that's why when you try to do this in all its generality, it becomes mathematically very, very, very complex. And that's what we're here to struggle with. But here's the deal. Replace that ball with light. So you're shining light through that rocket here. There's a hole that's opening. That rocket is accelerating. For us, we look at that light beam from the outside. The light beam goes straight through that piece of space. It's a straight line for us. But the people inside the rocket, because the rocket is accelerating, obviously, it takes some time. Light is not infinitely fast. It takes some time to cross through here, and it will therefore come out at a different position. If you're inside that rocket and have no idea what's going on outside, you would see a light beam coming in, and that light beam is bending downwards. Oop. Just like the ball did. Equivalence principle. And Einstein says, well, I cannot decide whether this is due to the acceleration or whether this is due to a gravitational field. And therefore, he says, light must also be attracted by masses. Light follows a curved path. And that's kind of weird because, yeah, especially with these laser pointers, right? We always think that light goes just in a plain straight line. Einstein says, no, it follows curved trajectories as if there is an acceleration. It follows curved trajectories as if there is an acceleration once you have a gravitational field. That was a revolutionary idea. And he said, the cool thing is, and this is why we're here tonight, the cool thing is we can test this. Look, the sun is a very massive object, and the sun is influencing space-time around it in such a way that a light beam that normally would miss us from a star that's around here gets bent around due to gravity, and therefore that star appears to be somewhere else where we normally think it is. So what you obviously have to do is you have to take a picture of that star field with many stars in it when the sun is there, because then these positions of the stars get affected. The closer you are to the sun, the more of a shift there is. And then a few months later, you take the same picture of the same piece of the sky and you compare what happened. So these stars here, as you can see, they basically are in exactly the same position as they were before. But when you compare those, they've already been shifted here a little bit. And the closer you get to where the sun was, the more of a shift there is. And it's this shift that he says, we can measure that. We can go out, problem. If you want to take a picture of these stars while the sun is up, good luck. It's like taking a picture of a little moth that's illuminated next to a big floodlight. Have you tried that? Ever? Won't work. So you need to somehow dim the light of the sun. Well, what better idea to have the moon do that for us? And that's why you need to do this during an eclipse. So Einstein suggests this around 1911, and he goes around to a couple of astronomy friends. Initially, they're all like, nah. The predicted effect is very, very small. And furthermore, it turns out that Einstein misinterpreted his own equations. And up till the year about 1915 or so, he believed that deflection near the sun would be about 0.83, what is called arc seconds. So this little symbol here is arc seconds. It's a very, 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 very tiny, small angle. 1 arc second, and this is less than that, 1 arc second, take a dime. The apparent angular diameter of that dime is 1 arc second when it's about 8 miles away. So take a dime, go on a highway, straight 8 miles, put it down, and the top and the bottom is the difference between those two. Very hard to measure, and most astronomers were like, nah, this is 1911, we can't do this. Turns out that one of them thought, well, maybe we can do that, and this is Charles Dillon Perrin. He was actually born in Steubenville, Ohio, as I found out today. I didn't know that. At the time, he was the director of the Argentine National Observatory after he had had a brief stint at Lick Observatories. And he tried that out, and he had nice equipment made, and he wanted to do this during the eclipse that happened to go through Brazil. Brazil is famous for what ecosystem? Rain forest, right? So, rain. It was completely rained out. He couldn't see a thing, unfortunately. I mean, of course, he didn't go to the rainforest area. There are other areas in Brazil, but I mean, he was clever enough for that. But still, that's sometimes what you get with these eclipses. Famously, he was quibbling. He said that it wasn't so much that we enjoyed an eclipse, but we endured it, and that's how it was. Furthermore, a few years later, the same Charles Dillon Perrin was summoned again. This time, Findlay Freundlich was a great fan of Albert Einstein, a friend of Albert Einstein, and he got together 3 different expeditions from 3 different countries, from Argentina, England, sponsored Campbell, although he was American. So no, it was American sponsored, this one, and the German one. There's a great, nice eclipse that was supposed to be happening, and they stationed themselves, you can possibly see it, in Feodosia in Crimea. The eclipse was supposed to happen August 21st, 1914. It did happen August 21st, 1914. What happened a little bit beforehand? Oops, someone shot the Archduke. Germany is at war with Russia. Erwin Findlay Freundlich is interred as an enemy, is not allowed to do any observations. Turns out that both Dillon, Perrin, and Campbell are allowed to do their measurements, but they're not allowed to take home their equipment. The equipment was confiscated, apparently because they thought it may be war relevant, and it's now stuck. That special equipment is now stuck in a few minutes. It turns out that this was the very first time that Perrin managed to take a photo, but that photo turned out not to be good enough to determine what he wanted to do, because this is a very, very difficult task, as we see in a few minutes. Well, then comes not yet the big expedition of 1919, because now this saga continues. Turns out that Campbell and Curtis, that is basically going across most of the United States. And the United States at that moment is basically the only country that is not so war-torn that they thought that they have a good shot at that, except for the fact that, remember, their equipment, at that moment, it had been transported to Vladivostok and then to Kobe in Japan, and it was stuck in Kobe, and they couldn't get it off there because there was war transports, and they said, well, we can't transport telescopes right now. So they were without telescopes. They had to borrow telescopes, and they did manage to take a couple of good pictures. The problem was that they were fighting with each other over how to interpret them. The interpretation of these photographic plates is not easy, and it took them several years, and they never, ever published anything. The US Naval Observatory also had the great idea. They even spent $3,500, which in today's dollars is quite a lot of money on specialized equipment, and they were somewhere in Oregon and were also completely rained out. So in come the English. And they are financing, lavishly, a set of 2 expeditions for the year 1919, where there's supposed to be a good eclipse. That eclipse was supposed to be very, very promising. We'll get to that in a second. It is not exactly clear why the English astronomers were so absolutely keen about this. Because remember, Einstein, whose theory they're ostensibly testing at that moment, not only was working in Germany, in Berlin during the war. He didn't really contribute to the war effort, but there were really big animosities between the scientists that had developed around that time. But also, you have to imagine, I mean, if there is one sacred scientist in England, it's Newton, right? And Einstein comes up with a theory that basically supersedes Newton's theory. So it's not exactly clear why they were so keen of testing this. They could have said, let's not do that because it may be the end of Newton's greatness with the theory of gravity. Another explanation is the following. It turns out that Arthur Eddington was really great. He was basically the Carl Sagan of the early 20th century for the English, and he popularized, under great, tremendous critique by other scientists, the theory of relativity. Some of those papers were smuggled to him actually through neutral Holland, and some of the scientists there gave him papers of Einstein that he then could translate, and he popularized, and he also realized that this is a very important theory. This basically turns things upside down for physics quite a lot, and therefore he really wanted to go ahead with this. He was a Quaker and a pacifist, and he had already claimed, he was also the director of the observatory in Cambridge, fairly high-profile position, and around 1917, the war situation became so dire that at the age of 34, he was supposed to get drafted. But he had already declared more or less publicly that as a Quaker, he cannot do that, and he's a conscientious objector. The university didn't really want this to become public because that meant a big conflict. At the time, he was fairly popular, and it would have either ended up in him being drafted under protest, or he basically making a big stance against the war. And so what they did was they convinced the generality that, oh, this mission is actually important enough that we need to come up with a big expedition, and the planning of this expedition to many, many politicians pulled some strings, and they were able to basically keep him out of all of that. So there's a real political issue here as well. That eclipse, however, was very, very promising. Why? Because it turns out that that eclipse happens to be at a time when the moon was what is called perigeuum, very close. So the moon's orbit is not a circle. It means sometimes the moon is closer to us and sometimes it's farther away. It just so happened that for that eclipse, the moon was quite close to the Earth, and that means that the Earth is going to be in that shadow for a longer period of time. It was a very long eclipse, more than 5 minutes in certain areas. So ours will be at maximum 4, so that was a good minute longer. And when you need to take quick pictures, remember that is what needs to be done. So they need to be taking quick pictures. That is a definite advantage. Another great advantage was realized when they figured out that, oh, at that point of time, the sun would be near the Hyades, which is a cluster of bright stars. And that means that in the vicinity of the sun, you will now find fairly bright stars. Because it turns out that even with the equipment of professional astronomers at that point of time, this was going to be a challenge to detect those faint stars during an eclipse, because you cannot take long exposures, because then it gets so blurry that you don't know exactly where the stars are. They sent out 2 expeditions, one to a place called Sobral in Brazil. In that, they had 2 instruments which they had to loan out from the Irish, actually, so there's an Irish contribution in this as well. And it turns out that they were fairly successful in taking a good number of exposures. About 19 with a big telescope, and 8 that had at least 7 stars on them with a small Irish telescope. That turned out to be a blessing in the sky, basically. The best pictures came really from that one. What you also have to do, as I mentioned, is not only do you have to take pictures at the time of the eclipse, but you have to look at the same spot in the sky later on to do that comparison, whether the sun has been bending the light or not. And so they returned later on, and therefore, it took them quite a while to get back to Greenwich, and they delivered their plates. So here's a little bit of how this looks like. So this is the actual equipment. It's actually kind of interesting because it turns out that, so these are these 2 things that are called solar stars. Basically, what you're doing is you're projecting the sunlight with a mirror into the telescope, because at that point of time, these telescopes, they had enormously long focal lengths, like 16 feet or something like that. These are beasts. And if you need to hold them stable while you're looking at the sun and you're tracking them around, that requires very large mounting. And that very large mounting simply couldn't be transported into the wilderness of Brazil or, as we see, outside the coast of Africa. And so they came up with this solution of projecting the sun right into this. And all that they had to do is move that mirror here. That's much easier than moving the whole telescope. So it's a clever thing. This is an actual picture that they got. Whoop. Not a very good picture. You actually have to look very carefully for the stars, and you see that, oh yeah, there are some, so this is an artifact. There are some, but they are tiny little dots, and they seem to be moving around, and oops. This meant that the whole endeavor of really figuring this out precisely is terribly, terribly difficult, even for professional astronomers. The expedition that is more famous in some sense is the one that went to the west coast of Africa, led by Eddington. They only had one instrument, and famously, of course, as always in these circumstances, there's a thunderstorm right at the morning of the eclipse. The sun clears up a few minutes beforehand. Frantically, he goes around. I would have hated to be the astronomer having to take the pictures, because he wasn't able to look at the sun. This is the great thing. You want to see the sun and the corona and everything and experiences. No, he was busy taking the pictures for this. And so he was hoping that some of those would turn out to be good, and we'll see. So they're back in mid-August in England, and they're beginning to analyze the data. And they immediately realize how problematic this is. You have to control for a lot of things. These deviations, so these photographic plates are 16 by 18 inches, and what you do is you lay them on top of each other, and then you need to kind of rotate them in such a way that you see whether the stars are in the same position or not. Sounds easy enough for us, but in order to do this precisely, remember, the angles that we're talking about here are the size of a dime at 8 miles of a distance. This is really, really difficult, and a lot of things can go wrong. Specifically, you have to take images of the sky at very different conditions. When you were doing this while the sun was up, it was warm. Later on, you take the same patch of the sky in the middle of the night and it's cold. That usually already is enough of a variance that your photographic plates at that moment vary quite a lot. And they had to control for all of these factors, and that's why it took them several months. I mean, you would think that, okay, took a picture, 2 of them, overlay, there it is, measure it, done. No, it's much harder than that. And it turns out that they came up with totally different values for it. Einstein had predicted this deviation, and what they measured, as you can see, is not exactly that. So they weren't totally clear how to announce that, and they went over that procedure over and over and over again. But finally, in November 6th, so about a year after the end of hostilities of the First World War, there's this dramatic meeting at the Royal Society, a really cool place, and they had basically created this frenzied atmosphere where they had leaked to the press that, oh, there will be a great announcement. So everybody was waiting for something, and it turns out that under the picture of Newton, so famously there's this portrait of Noller of Newton. So Newton was watching all of this basically from the wall, and Einstein's predictions. So that's it. The national hero of Britain gets demoted. It's like, whoa, that causes some waves. And of course, you can imagine that the reaction within the scientific circles was at least ambivalent, to say the least. So first of all, a lot of people questioned the data analysis. They said, whoa, can we really attribute this to the right effect, and is it really the right way to do this? It actually turns out that there was a very long debate afterwards whether basically they accused Eddington of cherry picking, throwing out some data. Oops. So as you can see here, these observations here with a large telescope in Brazil, they're actually much closer to Newton's value than to what Einstein predicted. And they basically ignored them. They had good reasons for that, but there's a long debate whether this was justifiable or not. And so, unfortunately, this also led to a campaign in the 1980s by some authors who completely questioned the validity of Eddington as a scientist, and they were totally wrong. So this is, luckily enough, now basically done and dusted, and everybody knows that that was the right. They actually did a very good job, especially given the circumstances. More importantly, possibly, and we'll see this, is that the hostilities between the German scientific community that was basically banned from any collaboration worldwide because of the First World War, after that softened a little bit. They became from being total pariahs to, well, yeah, Einstein, okay, well, we can talk about them. So that was actually something that Eddington was very, very adamant about. Unfortunately, in fact, those results within Germany were used by certain circles to completely discredit Albert Einstein, basically accusing him of plagiarism because there was a result earlier that had been predicted by another physicist, and physicists around the group of Lennard or so, these Aryan physicists. That was a time to come, basically, and you could see the shadows of that already looming large, unfortunately. The media, however, was very, very enthusiastic, surprisingly enthusiastic. Again, this is a totally bizarro, outlandish theory about the deflection of light on a level that nobody else would ever see unless you have really, really, really specialized equipment under really, really specialized circumstances. What's the big fuss? Well, the news was that the London Times had on the front page had this. It actually turns out that it's not exactly on the front page, but they had a very nice article and a very, very strongly worded article that caught the attention of everybody. It turns out that in that case, the scientists themselves were clever enough. So Dyson and Eddington had basically stoked the interest already over a long time, and they had talked to the press basically without. Instead of the other way around, the press didn't come and say, hey, what are you doing? No, they went to the press and told them this is what's going to happen. So actually fairly clever PR. Turns out that it actually was on page 12, somewhere on the corner there. So the story about the American publication, the New York Times, a couple of days later when a cable was sent over, opened up slightly differently, and the tone is quite different. The story is that part of this was basically fabricated by a sports reporter who didn't exactly know what was going on, but he was the one on duty when that cable came in, and he came up with, I mean, look at this, I mean, man of science, more or less agog. I mean, no, they had carefully prepared all of this. So this theory, however, it resonated with people for some strange reason. We don't exactly know why, but there were dozens of publications. Here's the New Londoner that actually had a long report on both of those missions and how it was measured and what was going on there. So it was in everybody's mind, and surprisingly, it lingered for a long, long, long time, despite the fact, or perhaps because of the fact that nobody seemed to understand what was going on. So when you asked the people, they were not able. Einstein's fame after that rose like a comet. He became the very first science superstar. On his first journey across the Atlantic on the steamship, when he arrived in Hoboken, it was amazing. It was like a big celebrity arrived. There were more than 5,000 people. The reporters actually rowed on their boats towards that steamship, and dignitaries awaited him. He gave a lecture series in Princeton where they had to move it to a couple of bigger auditoriums for the first day because there were more and more people showing up, including lots and lots of women dressed in fur, and people were like, what is going on here? On the second day, there were many fewer people, and on the fourth day, when he was deep into the theory, there were 2 or 3 people in the audience who still followed what he was saying. So Einstein himself never also fully understood why all of that happened to him. Towards later years, he is quoted with, it's bizarre to me. This is such an outlandish theory that has nothing to do with the everyday life of any person on this planet, and yet, for the longest time, people were extremely interested in that. I'm not so sure whether he understood that probably they were more interested in him rather than the theory and how quirky he was. I mean, famously, he ran around, he hated socks, right? And so he was running around in sandals all the time. And he had these famous quotes. He was extremely witty, and he knew how to say things so that it caught the attention of people. So sometimes I think it is a little bit tongue-in-cheek when he says, oh, the theory is so interesting, I don't understand why people are so interested. Well, they weren't interested in the theory because it turns out that most people really have no clue what it's about. If you are interested in these types of histories, I can highly recommend, there's a BBC, it's not really a documentary, it's more like a dramatization that aired a couple of years ago, I think 2009 or so. It is unfortunately not available for free on the BBC iPlayer, but I think with a Max subscription or so, you can find it and you can see it. If you're cleverly Googling it, you may actually get most of it on YouTube somewhere. And it's actually really, really nicely done. I've seen it a couple of times. We actually showed it once at a cinema. It turns out that it's a dramatization, so not all is correct scientifically there, but you see that the big conflicts about how to behave in a war situation when your country is at war and you want to do science. So I can highly recommend that. Now, that whole theme, in fact, 100 years later is still alive and well, because here at Ohio State we are doing something that's very, very similar to that. So it's called gravitational microlensing, and it's exactly the same effect, and we use that to very, very good use. So the idea is the following. Replace the sun with another star that's far away that we normally cannot see, and there's a background star, and the light of that background star gets bent around that foreground star. It works like a lens. That's why it's called lensing. It's a very small effect, that's why it's called microlensing. It happens because of gravity, just like Einstein said. That's why it's called gravitational microlensing. And what that means is that, oh, look at this situation right now. Normally that starlight would miss us completely. Normally that starlight would miss us completely, but now part of it gets to us. That means that when you follow that background star, how bright it is, sometimes when the bodies align really nicely, and there's a foreground star that is just in the line of sight, you will get more light. That star will suddenly become brighter for no reason whatsoever. And what you can conclude is there must be a foreground star. Okay. What Professor Andy Gould realized was, this is actually awesome, because not only stars can do that, but imagine there is a planet orbiting around that star. That planet also is massive, and if it aligns properly, it will actually influence that light curve. And instead of looking something like this, there's now this little bump in here. And that is how you can detect the presence of planets around other stars. It's one of the fascinatingly cool methods that was developed here at OSU. At the moment, we have detected 89 planets. What you have to do is you have to monitor hundreds of thousands of stars all the time and see whether they get brighter randomly. And then you need to trigger an alarm, and it's super exciting when you are at a telescope and you're part of that network, because you have to monitor it all the time. Which means that if you're in one place, sun comes up, nah, not good. Therefore, you have to have telescopes all around the world that can basically continuously monitor all of this. And when you're part of that network, sometimes, as you can see here, these data, this is what is called a light curve. And there's exactly this is happening. So this is this little bump here. And when you're in one of those telescopes, you get constantly bombarded by phone calls. You need to observe this now. Put your whatever you've been doing before, put your telescope there, and there's a lot of frenzy, and You go to bed after your observations and you prepare for the next day, and you wake up and you open your email and there are 50, 100 emails like, and it's really cool. It's a lot of fun. And so that's what we do. And that's basically the leading group called Microfun. And it's really, really amazingly cool that we are still using basically the same technique that Einstein discovered, the bending of light around massive objects. Now, to stop, I have a question for you. Have you ever in your whole life used the theory of general relativity? Who thinks they have? All of you, probably. All of you. Huh? These modern phones, they're awesome. GPS, so that you know where you are. The GPS system is the only technical device that I know that must use the theory of general relativity. The way that it works is, the general principle is that around the Earth there are a couple of satellites. They all send out timing signals. And basically your GPS receiver receives the signal that, oh, I'm that far away from this satellite, I'm that far away from that satellite. If you are that far of a satellite, well, the satellite could be anywhere on that circle. If you know that you are that far away from a second satellite, all of a sudden, you can only be either here or here. And if you receive a third satellite, you intersect 3 circles, and that can only intersect in one spot, and that's where you are. That is how GPS works. In order for this to work properly, you need to time those signals extremely well. They travel, obviously, not quite with the speed of light, but they're electromagnetic signals. And if you do not take into account that the Earth is massive enough to bend those electromagnetic waves, you're off by miles. So you walk home and you look at the map and you know where you are. Thank Albert Einstein that he figured that out. Thanks. Okay.
Thank you. Thank you, Dr. Frank. If anyone has any questions, if you raise your hand, I'll bring the mic over to you. We did have one come through online. Someone asked, was Einstein in conversation with any of the scientists, either leading up to their studies or during, to help them?
Yes. So famously, he actually approached some of the astronomers. There are 2 other big tests of the theory of general relativity that can also be done with astronomy. The one was already done beforehand, and it's about the precession of Mercury when it orbits around the sun. There's something unusual about that cannot be explained by Newton's laws, the way that they're set up. And so that was tabulated already, so that was well known. Another one was called gravitational redshift, and he always talked to astronomers because he realized that astronomy can make valuable contributions to this. Initially, all of the astronomers were like, yeah, this is very hard to measure and we don't know. And by the way, your theory is so bizarre that we don't even understand what's going on. Until Freundlich came along, and he was totally on fire. And that's when it really kick-started. And so, yeah, he was in contact. He, in fact, so Freundlich, that expedition to Crimea, Einstein came up with personal funds and also with funds from someone else. So he asked people to contribute to that. And he was in, there are these famous lines where it was said that, so he was apparently, when that result came in, he was fairly nonchalant about it, like, oh yeah, I told you so, right? Yeah, and he was asked, so what would have happened if God had decided to do it differently? And the quip was always that he said that, oh well, then I would be sorry for God because my theory is correct. And he was not shy in doing these types of things. But it actually turns out that he had a vital interest in all of this. And so he was talking a lot with other scientists and astronomers during that time and kept talking to them. So this was only the start because, as you've seen, the data analysis and all of this was not watertight yet. And they had other problems with this redshift of gravitational redshift of stellar spectroscopy. And a year later, there was an eclipse in Australia that they had many more stars that they did, and so over the next 4 or 5 years, it really confirmed that, and so he kept up with that all the time. Yeah.
There's a comet that's going to be close to the sun during the eclipse.
Yes.
Would it be safe?
So yes. However, personally, I wouldn't try to do that. No, because the most important reason for that is the clock keeps ticking very fast. The eclipse happens, and you want to enjoy that mostly with your eyes. If you're trying to figure out where something is, you're wasting valuable time. Unless you know beforehand where that comet is, really, then by all means, quickly do it, because the comet is not very bright. At that moment, when there is totality, it is actually totally safe, and you must take off your glasses, because otherwise you're not going to see anything. So at that moment, it is totally safe to look at other things. They're not going to be super bright. There are all 5 planets that are normally visible to us. They are around, so that can be that may actually be really spectacular. But I wouldn't use binoculars or so for watching that. Except, I mean, that comet could be interesting in that we normally don't see that. But as I said, I'd be first enjoying the first minute of it, and then maybe if you have some time and the conditions are good, yeah. But it's totally fine.
Well, if we know that mass can bend the light, do we know whether dark matter also would exert a gravitational force that would bend light?
Yes. So that in fact is a characteristic of dark matter, that it also does that. Unless you go to really bizarre theories that don't predict that, so it's not really anything special about matter. It's the fact that space-time gets distorted, and light follows that just as if it were a particle. So it has no choice, basically. It follows the shortest line between 2 points, so that it's the shortest time duration, and that means it needs to go on a curved line. And whether that curvature comes from regular matter or dark matter doesn't matter. Doesn't matter.
Well, thank you, Dr. Franck. Another question. Yep,
yeah.
Here we go.
You mentioned that his theory was proven in the 1919, 1914 time frame. Are astronomers still trying to refine his theory
Yes.
based on technology marches on?
And this is one of the remarkable. So the question was, to repeat it, the question was that the theory, well, in some sense, you can never really prove a theory. You can only find faults with it, basically. So that's the way that science actually works. But so far, we've done many tests, and it's amazing how precisely the theory predicts what we then observe. So recently, we've seen images we've taken images of black hole, now cases where we detect gravitational waves of very massive objects that are spiraling around each other and then are collapsing, and that causes ripples in space-time, basically. And Einstein, without knowing anything about this, his theory predicts this very precisely. And at the moment, we haven't found anything